Hello guys, following the previous lessons on VIVADO HLS interfaces, today we're going to learn how to use the AXI for stream. Basically we're going to learn how to infer an IP core that uses as input and output the AXI stream interface. Hope you guys enjoyed. I'm going to switch now to the board and explain a little bit what will be the lesson of today. Hope you guys enjoyed. Bye bye. Okay guys, VIVADO HLS AXI stream interfaces. Okay, first let's start why we should use the AXI stream interface. So IP cores that uses AXI for stream interfaces are ideal cases for filters and image processing filters. Basically, any IP which should have an output at every input that arrives is a nice case for an AXI stream. Okay, how you connect the AXI stream blocks with the zinc? Okay, normally no. You normally always should use a DMA. Okay, actually you have the zinc that is going to that you need to enable the high performance slave port. Okay, then through an interconnect, the DMA is going to push data directly to the DDR. By the way, without using resources of the CPU, but anyway. So, and in the DMA, you're going to have the master memory mapped to stream that is going to push data from the DDR to your IP core, okay? And the slave stream to memory mapped is going to receive the results from your IP core, okay, directly to be pushed to the DDR, okay. Again, all this without using resources of the zinc, which is quite cool, okay. Another nice feature to have is that not only having an IP with only stream ports, okay. Normally you have the IP with some parameters that are controlled through an AXI-like interface. And this is exactly what you're going to see in the lab. We're going to create like a simple IP core that is just going to multiply the stream that is going in by some parameter, by some gain. And we're going to see how to do this in the lab quite short. Okay? So, remembering again, use the AXI stream interfaces if you're going to create, for instance, convolution filter, FIR, or really some kind of algorithm that falls nice in this stream behavior, that you push some data in and you want to have immediately some data out. Okay?
Hello guys, so let's analyze this IP core which uses the AXI stream protocol. Okay, so first of all, let's start just taking a look on these headers. Okay, and actually they are not mandatory to use AXI stream, but actually it is a set of classes of VIVADO HLS which enforce you to use good practice on creating IP cores. Okay, for instance, the HLS stream obliges you to read your stream once. Okay, and if you want to have the same data again, you are obliged to cache this value, which is a very good thing to do in FPGA. Instead of you to read it again and again on the same interface, if you need to read this interface, the value of this interface more often, you cache it. Okay, so basically what we're going to do is a simple IP core which has an input stream, an output stream, and a gain. Okay, the input stream and the output stream here we are forcing to be AXI stream. Okay, if you don't use this, it's probably going to synthesize as FIFOs. Okay, but by doing this, you're basically telling VIVADO HLS that you want to use the AXI stream interface. Okay, the gain parameter we are choosing to be AXI-Lite. Okay, AXI-Lite slave, and the whole function we are also saying that we want the AXI-Lite interface. As we seen before, by using this return, actually we are going to get the signals done idle, you can start your IP core, you can control all this through the AXI Lite interface, which is a good thing. Okay, so the code is quite simple. It's just a for loop, okay, that go from 0 to 1000. By the way, this is needed by VIVADO HLS. VIVADO HLS need to know more or less what will be the final size of your IP core. I mean, there is no dynamic allocation, okay. This HLS pipeline is a primitive that we're going to see in the future. It's basically force your for loop to execute faster, to have more throughput. But we're going to explain this later. Okay. So basically, what it does, we read the stream, okay, and this, by the way, will be blocked until the FIFO while the FIFO sender is empty. This you can imagine that is going to be blocked. Okay, and we create here a variable of the type axis, AP axis, which means we want to use the side channel type of the axis for stream, which by the way is really important because it's going to include the T-last signal. It includes more signals, okay, but most important, the T-last, which indicates that the stream is over. Okay, so basically, what we're going to do, we read the data, okay, and then we say that the variable vol out will receive vol in dot data multiplied by some gain, okay, and then we just copy the other side channel variables, which are the signal keep, strobe, ID, destination, and last. Okay, and in the end of the for loop, we push it on the FIFO the value that you're reading, which by the way is going to be blocked if the FIFO receiver is full. Okay, so let's save it. We're going to synthesize. Okay, guys. So now that the synthesis is done, let's analyze it. Basically, the latency here, as we seen before, the latency is the number of clock cycles, in this case of 10 nanoseconds, that it takes for this whole 100,000 elements to execute. Okay. So the utilization is quite minimal. Okay, and here the most important is our streams. Okay, so here is the input stream that you have t data, t valid, t ready, t dest, keep, strobe, user, last and ID, and the output t data, t valid, t ready, t dest, t keep, strobe, user, last and ID again. Let's just talk a little bit more about the stream interface. The stream transaction starts when t-valid and t-ready are high, okay, and the whole stream is marked to finish when t-last is asserted, okay. But we're going to speak a little bit more on the AXI stream alone when we created by hand an AXI stream IP core, okay. So the IP is created. Let's just simulate it and see how it works. By the way, let me just open the test bench. Okay, so the test bench is quite simple. Okay, let me close it. Here we define the input and output stream. Okay, we push into the input stream some values, in the case from 0 to 1000. Okay, and then we call our function and we pop, okay, the results from the output stream. Okay, which by the way is this result here that you have. We're calling our function with the gain of 5, so 0, 5, 10, 15 and so on. Okay, guys, so let's go simulate our design. Let me just to dump trace, and let's use module sim because we want easily to open the waveform. So guys, the code simulation executed, okay? And well, in theory, now in the directory sim verilog, we should see here the output do gain.wlf. So you can use this file in model sim and open to see the waveform, and this is what we're going to do now. Let me just pause the video to open model sim. So guys, this is the simulation on Questa sim, actually, not model sim, sorry. So one thing that we can see already is that, look here at we know that the gain is set to 5, okay? So actually this output is referent to this input here, and we can see in order to get this output, we took 1 2 3 1 2 3 4 5 6 ticks of clock. And if we open again HLS, we can see that our latency is actually 1006. Okay, so we really have a latency of 6 clocks when to have the stream starting. So we really lose those cycles here. Okay. Other thing that is nice to mention is let's just take a look on the AXI Lite interface. Let me just change the format here to actually unsign it. Let me so again unsign it here as well. Let me just do a zoom. Okay, here in our wdata channel, you can see that at this point here that we add our gain. Okay, actually this is at the address of the register. Okay, it's like 2 bytes later. Okay, and here is our actually, when we set this to 1, is our start signal. Okay, and then after this the IP core is going to execute. Okay guys, so let me switch now to the most important. Now we're going back to VIVADO HLS and we're going to export our IP, okay, and use it in VIVADO. So basically now we are going to create the project that for our Z board that use the zincs. Okay, as we saw in the board, we're going to use also the DMA, and well, let's see on the lab on the screen. Showing is easier than talk. Okay guys, so let's just add our zinc processor. Okay, and cool, and we run the block automation. I'll try to do this as quick as possible because this is actually always repeated, and we actually did now count of thousands of times. So the repository is already set. We're just going to add our do game block. Okay, so do game. Cool. If you run design automation again, the control part of our IP core, which is actually in AXI stream, is going to be connected. Now we are going to enable the high performance port of the zinc, and we are going to use this to connect to the DMA, which is quite fast. We just come here to HP slave, we enable this guy here. Okay, now we're going to add our DMA. Okay, direct memory access, AXI direct memory access. We're going to configure the DMA to be simple and allow unaligned access. Also here we're going to add the maximum amount of transfer possible, 23 bits of transfer. Cool. Now we run the connection again. Let's connect first the control part of our DMA, actually also in AXI Lite. Cool. Now we connect the high performance port of the zinc with the DMA. Cool. Now the output stream of our, let's go through the input first. The input port of our IP core is going to connect to the master axis memory map to stream, and the output stream of our IP core to the stream to memory mapping. Okay. Let me just zoom out. Okay, there is something that is missing as well. We have here some interrupts, okay, and we want to control this in our zinc. Just run the connection automation just to connect any other missing signals. Cool. Now this is done. So let's enable the interrupt on the zinc. So go to interrupts, fabric interrupts, PL to PS. Okay. Actually, we have the interrupt of our IP core and some interrupts on of the DMA as well. So if you want, you can concatenate them. Okay. So actually here we have 3 inputs. You just want to put, so this guy will be connected to our interrupt. Let's just do some auto route here. So we have this interrupt here, and we also have the interrupt of our IP core. Cool. So we organize again, we do a little bit of more zoom, and basically that's it, guys. We can validate just to verify if we miss something. Cool, everything's fine, validation successful. Okay, so at this point we can just generate bitstream. This can take a while, and since it's out of date, cool. And I'm going to pause the video, and when it's done, maybe I just lose a little bit more time to explain how the DMA is connected, and then we switch to the programming part. Okay, guys? So guys, just to do a quick review on how to use the AXI stream with the zinc. Okay, I just maximize a little bit here the model, and let's take a look. So first thing, we use the HP port on the zinc. Okay, this stands for high performance port. Okay, and actually this port here is going to be sent to an interconnect. By the way, this interconnect will be added automatically. Okay, and this will be used, this interconnect will be used to control and to receive data in these ports here of our AXI DMA. Okay, actually this stands for master axis memory mapped to stream, and the other part is master axis stream to memory mapped. Okay, so basically also let me just click twice in the just to show that how we configure the axis stream. Basically this guy here controls the amount of data that you can send per transaction in the DMA. We enable the read and write channel. We enable also just the simple mode. We are not using scatter and gather yet, but we're going to learn this in the future. And we allow unaligned transfers. Sorry, bad accent. Okay. So basically, the DMA will push. It will gather data from the DDR of the zinc connected to the zinc, and then you gather data from the DDR and push into the into the input port of our IP core. Okay, so here the master axis stream memory mapped to stream, will stand just for gather data from DDR and push into the input of our IP core, okay? And he's going to receive data from our output stream to the slave AXI string to memory map port, okay? Uh, our IP core has some control interface in this, in this port here, okay? Actually it's connected to this interconnect. If we follow along, this guy will stop in our zinc. And we use the master general purpose port, okay? How we define those ports? We just click twice, okay? Then we go to PSPL configuration. Here we define the general purpose port, which we use to control our IP core. And here we define a high performance slave AXI port, okay? This, by the way, is not AXI stream. Microblaze allows to have AXI stream ports, but in this case is really another AXI full in this case, but slave. And we use this to connect to our DMA. Okay, guys. What else? Basically, we are also using here the interrupt, but probably not going to use that in the code yet. I don't know yet how to use. And basically, this is just to indicate that the IP finish its operation. Here as well is some interrupts from the DMA, and we just use a concat block to concatenate all this and put on the interrupt port of the zinc. Basically, we just click twice as well, and we define it here in interrupts, fabric interrupts, PS, PL, PL, PS here, because it's the PL part who is going to indicate that an interrupt occurred in this case, okay? And well, basically that's this, guys. This is the part on Vivado alone that we use to use the AXI stream, okay? What else? This is important as well. Okay, I will switch to the Xilinx SDK just to show as well how the source code, how to program your zinc in order to use the DMA to exercise our IP core. Okay, let me just pause the video and I switch to the Xilinx SDK. So guys, basically the Xilinx SDK part to use the DMA and RP core is quite simple. Okay, here we just include our drivers for using the DMA, and this is the exported driver from Vivado HLS. If Vivado HLS detects that you use AXI Lite, he's going to create a simple driver to help you control your IP core. Okay, here is just the configuration interface is needed. This is an important point. Let's wait a little bit and have attention here. So basically here we just defining our place in our DDR that needs to be kind of far away from your code, okay? That's going to be like the scratch pad of our DMA. So basically our DMA is going to work on this address, and it's important that you don't want to mess this, or you don't want to put an address that is near our code, basically because if you do this, the DMA will basically screw your program. Okay, here we are defining on the BSS part, I'll explain this later, an array that is here is going to be the input of our IP core. This is the function that we initialize our cores. In this case here we are initializing the do gain IP core, the one that we created in Vivado HLS, and this we are initializing the DMA. Okay, this structure will always be the same. In the end I'm going to upload as well this code, so you really don't need to do a pause and type all this. I'm going to share this as well. Here we just disable the interrupts. Okay, we are disabling the interrupts that go from device to DMA and DMA to device. Okay, and okay, so we have these pointers here that basically is going to be the TX and RX pointers of our DMA. Okay, we just populate the input stream here. We put from 0 to 1000. Okay, more or less what we did in the test bench. Okay, and basically here we are putting a while just to exercise and keep using the IP core, but basically this is what we're doing. Here we're just setting the gain, okay, to something that the user will input. Okay, this is an important part as well. Here we are just invalidating or flushing the cache in order to avoid that your zinc is seeing some data but actually the DMA is seeing the other. So here we're just forcing to really to discard what you have in the cache. Okay, and in this part here we are going to transfer, okay, our input stream, okay, to our IP core. Okay, this is the DMA to device part. Okay, so basically the input stream is going to the input stream data is going to be sent to our IP core, and at this part here, the device to DMA, we are going to read from our reception buffer of the DMA all the data which is outputted from our IP core. So here we send the data, here we receive the data. Okay, and I just did a while here that is going to be blocked until the IP core does not send it till last. Okay, and here we invalidate the cache again, because basically this reception buffer could hold some cache from the zinc, and we don't want that. We really want to read what is in this part of the memory. And while our IP core is not done, but basically this has been done way before when we unblocked from this part here, and we just print the data. I'll just connect now my zinc and show you guys how the whole thing works. Okay, I'll pause the video now and let's see. Okay guys, now that we have our microblaze connected, sorry, not microblaze, the zinc board, the Z board connected, we're going to run our software. Okay, and you see it's quite simple. First thing is going to ask for a gain, for instance 5, to keep the same as what we did in VIVADO HLS, and basically we got the same results. So let me just scroll up. So basically you're just multiplying everything by 5. Okay, so guys, this is enough for today. I hope you guys understood that how to use AXI stream cores. Remember that in order for you to use with a microcontroller, or being the zinc, the PS part, or even the microblaze as well, you may need a DMA. Okay, and the job of the DMA will be to gather data from your main memory, send this data to your IP core and gather the results. And by the way, is a DMA, your CPU are not going to actively doing this, so you can do, your CPU can do other stuff while this calculation is being done. And hope you guys enjoy it, and the next video I'm going to talk now about AXI masters, and that's it guys. Basically all the AMBA main IP cores we cover in this training. Okay, I hope you guys enjoy it again, and see you guys in the next video.